That's all I got to say about that. So I want to give, so last class we talked about Lindemann Hinshelwood, about unimolecular reactions. I want to just show you another example of where we can apply this idea of collisional deactivation, that in these reactions, that the thing that really drives them forward isn't the reaction itself, but the fact that the materials can collide with objects to get excited and to de-excite and relax products. Right? You need two processes. There's a collision process and a reaction process. I want to look at one more example of that where we apply the same idea that teaches us something really interesting about a different class of reactions than the ones we're looking for. So the last thing we looked at was just taking a molecule and having it fall apart, in a unimolecular way. But we can apply the same ideas to reactions with multiple molecules. And the example I want to look at in particular today, very briefly, just a short aside, is the process of combining two free radicals together. So I want to look in particular at radical-radical reactions, where you have two reactants that have unpaired electrons, right? So that generally, the general idea is that you have A with an unpaired electron and B with an unpaired electron combining to form AB. Okay. Shouldn't be hard. Convince yourself that this is very exothermic. Radicals are unstable, right? That's what we always learn, that unpaired electrons want to be paired, right? So this is not a difficult task energetically, right? The moment A and B see each other, they're going to react with each other. Maybe I could prove that to you. We can look at the thermodynamics. Let's just make sure that this is exothermic. Right? So my claim here is that delta H for the reaction is less than 0. We don't know anything about delta S yet necessarily because it depends on the reaction. But in general, that this is always going to be less than 0. And so let's look at an example of this reaction. One that's much more common in real life is the reaction of oxygen atoms with nitrous oxide. Nitrous oxide is also a radical. Right? This is laughing gas. And these combine readily to form NO2, nitrous dioxide, which is a toxic brown gas. Right. Oh, this also happens with O2. There's an additional step because you got to break that O oxygen apart to oxidize NO2. But you can get a similar reaction with O2 and NO as well. It's a little slower. Let's say it's an equilibrium. Of course, this is in the gas phase. It's the oxidation of laughing gas. This is the main decomposition route for laughing gas. And we can just look really quickly at the enthalpies of these. So I can make a little table of our reactants. So we have NO, O, and NO2. And our formation enthalpies at standard conditions for our species are plus 90.631 kilojoules per mole for NO. O has a enthalpy of formation of 246.844. And NO2 has a formation enthalpy of 36.781. So relative to the general constituents or the reference samples, which of course are N2 and O2 for this system, these are all higher enthalpy. Right? It's not surprising that O, for instance, is much higher enthalpy than O2. Remember, by definition, O2 has enthalpy 0. In order to make O, you have to break O2 apart, so the energy naturally increases, and each oxygen brings to the table 245 kilojoules per mole, give or take, which means that the bond between two oxygens is about twice that, about 500 kilojoules per mole. And so it kind of makes sense that these numbers are like that. And it's probably not hard to see that when we calculate the reaction enthalpy, when we take this number, 36, and then subtract the sum of these two, that this is negative. Because the sum of this is 336, and you're subtracting 336 from 36, right? So this is about negative 300 kilojoules per mole. So the reaction enthalpy at standard conditions is about minus 300 kilojoules per mole, right? So this is an exothermic reaction. Exothermic reaction, the energy drops. So we want to draw a reaction coordinate for this to think about the kinetics. So let's go ahead and do that. Our starting materials, we'll say start at 0 energy. We have NO plus O here, and the energy drops by minus 300 to form NO2. Okay, so there's our reaction coordinate. But of course, we haven't filled in the middle, right? It's not clear necessarily if the energy goes up or it goes down, or does it go straight down? Well, we can kind of argue the correct answer. And we'll see that experiment shows that this is correct. But my claim is that there's no activation barrier. There's no barrier. In fact, you could even argue it may have a negative barrier. That's a kind of a weird thing to say. But at the very least, I can argue that the barrier is 0. Why is that? Well, the fact of the matter is that we're reacting two radicals together. They have unpaired electrons. We know what electrons like to do when they're unpaired. They like to pair. So there is, in some sense, no energetic impedance for these two things to combine. There's nothing that's really stopping them. It doesn't have to do any work. In fact, they're in a situation that is unstable. Right? They want to get rid of those unpaired electrons. So they're going to release energy. They're going to release energy because there's some, in some sense, electronic strain in these molecules to stabilize that unpaired electron. They want to get rid of that. So the moment O and NO come together, they'll just react. They have no barrier. And that's generally true for radical-radical reactions. These are barrierless reactions.
Just to make sure, the y-axis on this graph is delta.
Is delta H.
Delta H.
Thank you. These are barrierless reactions, right? And that's generally true. I can't think of a radical-radical reaction that has a barrier, okay? They always come together without a barrier. So I could draw some curve that connects these two on my coordinate diagram, and it's just a downhill slope. It looks something like this. Okay, so let's think a little bit about the kinetics of this process. Let's apply the Lindemann-Hensel-Wood mechanism, which is that there's an intermediate that forms from a collision. That the N and the O come together to form a collision complex where they're very close together, right? And so N and O come together and they form something that's basically looks like NO2 excited. Right? There's this intermediate step that has the same energy of the reactants. And this kind of looks like O forming a bond with NO. Right? Some excited combination of those atoms. Remember, the energy is conserved. We haven't lost any energy yet. All I'm saying is that we're bringing NO and O together, and the energy doesn't rise when they come together. In fact, it falls. And so there's some excited energy here, right? This is NO2 with the amount of energy that the NO and the O bring to the table. And so some excited NO2 that forms. The bonds are stretched, they're vibrating a lot, but they're excited at that energy. And right, you have to relax it, right? So there's another step that happens where this collides or reacts and cools down to form the products. Right, so let's draw some mechanism arrows, right? We have some rate that forms the stability complex, right? That's like our collision rate, K1. There's a reverse rate, which is where they fly apart. And then there's some stability rate where the system relaxes down to the ground state. Just like we had before, right? Just like we had with Lindemann-Henschel.
Wait, so I actually had a question about that yesterday or on Tuesday.
Yeah, sure.
So once it becomes the product NO2, there's not going to be a K2 reversed because we're showing that there's a K1
Right.
and a K1 reversed.
Right. Why is there not a, I mean, there
Because
technically
it
could
needs
be
that
a
much
K.
more energy. Is that why?
Exactly.
Okay, I see. Okay, I
Exactly,
see.
right? Because now you, to get from here to here, you have a barrier
Right. Yeah. Okay.
in some sense, right? You have to go back there. So no hill, nothing's gonna roll back up that hill.
Okay.
And there's nothing to stop us from saying necessarily that this process is continuous, that this kind of moves smoothly through both of these steps. It's not two discrete steps that happen. I'm just saying that we can break it down that
Right,
way
yeah.
if we wanted to.
Okay.
All right, it's just a way to simplify the idea. These are not rates that we can observe, right? The point is that we only observe one rate, the NO2 formation rate. There's only one number that we measure in experiments, but if we can kind of like deconstruct that rate constant into a sum and competition of a couple of different rates if we want. It's just an arbitrary way for us to write things. Okay, so let's think a little bit about the kinetics about this. And again, you should be able to recognize that at low pressure, this thing is this complex, right? This is the thing that needs to stabilize to form the product. You need collisions to cool it. So a collision, right? And the Lindemann-Henschel example, we needed a collision to excite the reactants high enough to react. We don't need to do that anymore because the moment that the reactants come together, they have enough energy to react, right? Because they don't need any energy. Barriers. So they come together. Right, but you still need a collision step to take your collision complex and to stabilize it into the real molecule, to the stable molecule. So this is just like Lindemann-Henschel would. We need a collision step. So typically these experiments are done in what's called a bath gas, meaning that there's some unreactive gas that's floating in the background that's used as a pressurizing material, right? Maybe we use helium or argon, typically. And so what we actually need to think about is that we need that these reactions require a collision partner, right? So the rate limiting step, the slowest step of this process is not getting over a barrier. It's this thing being able to collide with something. So the rate determining step, the slowest step, is where this complex ONO excited collides with some gas atom, M, and transfers energy to it. Oh, sorry, O and O. This would be NO2. Right? Plus M. And in that regard, in this regard, when we have an additional collision partner, then there's an equilibrium.
Wait, what does the M stand for?
This can be anything that's non-reactive. Helium, neon, argon, N2, just something to collide with.
Okay.
A billiard ball, a dumb billiard ball. Right? These are what are called bath gases, right? Which are pressurizing material that is non-reactive. So there's actually an equilibrium because what we have here is a bath gas, this M, this collision partner, is exchanging energy with the excited state. Right? So to Angie's point, there is an equilibrium. well, we can work through the kinetics of this and do the steady state approximation and all that junk, but that's not really what we need to do. We know the conclusion about what happens here. This is no different than Lindemann-Henschel would, except in Lindemann-Henschel would, the collisional excitation happened on the reactant side, and here it's happening on the product side. So I don't have to do any math. I can just copy the results and use the same idea. And the claim would be that applying Lindemann-Henschel would that at low pressure, that the rate of formation of NO2 is going to be equal to K2, right? The collision rate times the concentration of M times NO2 excited. And this is second order, right? Because it has dependence on M and this as well. This is dependent on collisions between NO and O. So the higher the pressure, the more that gets created. And of course, this is the term that the concentration of your collision partner is related to the pressure, right? This is proportional to the pressure as well. So what you have is a low pressure that, once again, it's second order, that you need another body in the mix to stabilize. So this reaction is slow at low pressure. Okay. And at high pressure, of course, it reduces to first order. Second order. So this is a really interesting situation. Here we have a reaction that, you know, we go calculate in Gen Chem. I hate to keep bringing Gen Chem, I really do. But I mean, this is when we talk about this. But you bring it up, you say, yeah, I got two radicals. It's very downhill, very, very exothermic. And you can calculate that this is tropically disfavored because you're going from 2 moles to 1 mole. So entropy is going to decrease. But the entropy decrease is much smaller than the exothermicity. So delta G is negative as well. Delta S doesn't change that much compared to delta H. And this reaction, right? So you have everything that you would say is, well, this reaction should happen instantaneously. But in fact, at low pressure, it's extremely slow because, again, the excited state thing that you form can't find a collision partner to relax. So it just goes back to the products. So at low pressure, this is slow. Right, which is odd, right? Because you would expect that a radical recombination should be fast always. It's got no barrier. It's exothermic. It's delta G less than 0. Everything is asking, screaming for it to be efficient. But at low pressure, it's not. And so you look at low pressure environments, the atmosphere, space, you find tons of NO. You don't really find as many oxygen atoms in space, but or rather not in space, but in the atmosphere, most of it's O2. But NO, for instance, is a stable molecule, or it's an abundant molecule in the atmosphere. It's a part of the NOx cycle. Because again, the atmospheric pressures are low enough that NO can last a long time. It's even more dramatic than that. What about if we change the temperature? Right? We're at room temperature, we're at low pressure room temperature, and this reaction is going slow. So we say, right, when we've been thinking about, when we think about activation energies, if we have a slow reaction, we crank the temperature up. It needs to go faster. Right? And the reason why is because now your thermal energy that your reactants have is larger at higher temperature. And so their energies on average are closer to the activation. They're climbing up the barrier as you increase the heat. This reaction has no barrier. So what happens to this system as you increase the energy? Well, the enthalpy of NO2 and the enthalpies of NO and O increase, right, with their heat capacities. And these are, all three of these are gases. They all have fairly similar heat capacities. So you have over here 2 molar equivalent of heat capacities increasing the enthalpy as you increase the temperature. So this bar is going higher in energy, but so is this one, right? The enthalpy is increasing for NO2 as well as temperature goes up. But the thing is that you have 2 equivalents of heat capacity here, 2 moles of gas that have a heat capacity, and 1 mole of gas here. So that means that this enthalpy increases roughly twice as fast as this one. So what does that mean? That means at higher temperature, the reaction becomes more exothermic. Okay, well, that's good. That means that it should be even faster, right? It's even more downhill. You're gonna roll down that hill even more. Wrong. Because the energy at higher temperature, the energy increases, the change in energy increases, the gap gets larger, which means that your collision partner needs to remove that much more energy. And it turns out that it becomes less efficient at higher temperature. It becomes harder and harder for a collision to suck that energy out of the collision complex at higher temperature. There's a bigger gap between this point and this point. For efficient collisions, you want the gap to be as small as possible. You want a small energy gap because you just want something to come in here and whip that energy away. But the larger the energy gap is, the harder and harder it is to pull all that energy out. You might need multiple collisions to do it, right? You go from here, hit a collision, and then you hit here, and you hit another collision, and you get down here. So what happens is that high temperature, this reaction becomes even slow. So it's slow at low P and it's slow at high T. So ideally, if you want to make NO2 efficiently from O and NO, you want to do it at low temperature. Low temperature and high pressure. Right? That's in some sense a little contradictory to what you would think. But again, that's the difference between thermodynamics and equilibrium and kinetics. Thing is here is that we have no barrier, and that changes the thermal properties of the system dramatically. Low barrier reactions are more efficient at low temperature because the system has less energy. So, interestingly enough, we would want this to be at high temperature and low pressure. That would be the most stable way to make NO and O.
Wait, you mean low pressure?
High temperature.
That's.
So if I want to keep the reactants alive,
Oh, okay.
I'm saying that you want to have the reaction as slow as possible.
Okay, I see.
If you want to make NO fast, then you want to be at high pressure, low T.
Right.
Okay. This is a really interesting. So and this has been proven time and time again. When you go look at rates for radical recombinations, most of them are done at low temperature for this reason. It's just at high temperature, the reactions are just not very efficient. Do them at low temperature. A lot of them are done really low. 10 to Kelvin, 50 Kelvin, 100 Kelvin. Right above, around cryogenic temperatures. Okay. All right, so let me just look at a little bit of data from this. So this is an experiment that's been studied in detail for many years. And I just want to show you proof of this from experiment. I'm going to draw it. Okay, so let's look at the experimental data for this reaction. And what we're going to look at in particular is we're going to plot as a function our x-axis is going to be the concentration of NO per unit millimole. And our y-axis is going to be the observed rate divided by 10 to the 4 seconds. Okay, so these are the rates that we observe at different concentrations of NO as a function of the concentration. And let me put a couple of marks here. So let's mark everything out. So we'll put this is going to vary between 1 and 2 millimolar. And my rates are going to vary between, I think 1 and 2 times 10 to the 4. All right, sorry, I lost my mouse. Yeah, 1 and 2. So the top point will be 2, middle point will be 1, and 0.5, and 1.5. All right. And this is done at, I think, room temperature. I have to double check, but let's just say it's room temperature. Already, these are pretty slow rates, 10 to the 4. That means that these molecules are coming out every 10 milliseconds. That's a really slow reaction. Well, again, as I said before, another thing that I'll mention if I get a chance to, is that the rate of taking two, maybe you should also think maybe what would be the rate between two ions, plus and minus. Another thing that has no rate, right? Pluses and minuses attract each other in the same way that two radicals attract each other. You want a pair. It's a different energy. Plus and minus is electrostatic attraction. The attraction between two radicals is a slightly different, more esoteric interaction because they're two negative charges. But there's an energetic benefit to pairing those two electrons, spin up and spin down, and creating a pair, which is called the exchange energy. And that's the thing that drives it. So it's a slightly different energy, but it's a similar idea. And what you find in ion reactions, you take a plus charge and a minus charge, like a chlorine atom and a CH3 plus, right? CH3 plus and Cl minus to form chloromethane. Methylene chloride. No, that's CH2Cl2. Sorry. But I'll just write it here. So just a note. So if you take A plus and B minus and form AB, the observed rate you see for all of these is around 10 to the 12 per second, it turns out. It's always about 10 to the 12. There's actually a really interesting way you can derive that. But ion reactions have kind of a fixed rate. And so ions will interact very, very quickly. You'll make 10 to the 12 molecules every second with this math. And these radical reactions, right? This is also very attractive, downhill, barrierless, all of the same things as this reaction. The reactions are 8 orders of magnitude more slow. Kind of interesting. And again, this tells you something about the difference in attraction. There's a very clear attraction between pluses and minuses. And it's very fast to connect them together. They hone in on each other like homing missiles. But the radicals are much slower. It's a much harder process. Obviously, they don't attract each other in the same way. And so even though it's barrierless, they move much more slowly. So I think that's somewhat interesting. So let's just look at the results here. I'm going to make a couple of guidelines so I can plot this properly for you. So make a dashed line at 1.5 and a vertical line at 1 millimolar. Like this. Okay. And what we find is that at all pressures greater than 1 millimolar, we find that the observed rate increases linearly with increased pressure, right? So we have some plots here, some points. And it's a beautiful straight line, right? So this says that the observed rate is proportional to the concentration to the first power. Okay, first order. It's exactly what we would expect. Right? And then there's a critical temperature, there's a critical pressure where the collisions start to slow down and the collision rate becomes the thing that is the slows. We get the NO2 to relax. And what we find is that below this critical pressure, it starts out linear and then rolls off rather rapidly. That's a really bad drawing. I'm sorry. Let me try one more time. So the point is like right here. This. And so what we see is that no longer is linear, but instead it's a square. Right? So at low pressure, K observation is proportional to the concentration squared. Right? And that's exactly what we predict from Lindemann-Hinshelwood. At low pressure, the collision rate is the slowest thing. It requires two bodies. Right? So this is collision limited. Right? Down here, we're waiting for chemical molecules to come together and to collide with something. And on the right side, we're reactant limited, right? We don't have enough reactant to make it go faster. Okay, so even these bimolecular reactions that are barrierless exhibit the same properties that a unimolecular reaction. So we still need that extra body in there to fall apart. What I should actually write. Yeah, that's good enough. That's good enough. Okay, so Lindemann-Hinshelwood is a general idea. Collisions are necessary for transferring energy in and out of reactants. What's the whole point? Yeah, if you're doing things in liquid, there are so many damn collisions all the time that you don't really worry about these things. In the world of liquids, we're always here, generally. But it's interesting to think about how these reactions are ultimately limited. Chemistry doesn't happen on its own in some sense. You got to have a buddy to help you. There's got to be some sink of that energy. And that ultimately at low pressure and at the limit of slow reactions is the thing that ultimately sets your rate. How often do things come together and collide? Okay, so that's all about gases for now. I'm going to take a break from gases, and let's focus on something a little more. I don't want to say down to earth. That's not really what I'm going for. Something more biological, something a little more not practical. Let's say something a little more physical or natural. That goes that way, natural. So the topic I want to talk about today, and we'll probably continue into next class, is catalysis. Right, the use of a catalyst, which is 100% a kinetic property. And catalysis is a kinetic property.
It's like a new top, like a whole new subject.
Yeah, we're going to change subjects now. Yeah, no problem. All right, so let's first define what a catalyst is. All right, well, and again, whatever word you might have for a catalyst is probably correct. Right? A catalyst is a participating. Sorry, let me say this. I'm going to add participating in another word. Is a molecular substrate that does not appreciably contribute to a reaction's rate law or stoichiometry, but participates in a reaction by lowering its activation energy. What this means is that a catalyst is something, again, that participates in a reaction. It has a meaningful, let's say, a meaningful contribution to the mechanism. But it doesn't affect the stoichiometry. It doesn't affect the beginning materials. It doesn't affect the end materials. You don't put it in your balance. But what it does is it interacts with your molecules in the transition state. It becomes a participant in the transition state. And all a catalyst does is take the energy of that transition state and lower it. They reduce the barrier. Right? So really, so the idea is that, right? So without it, this is kind of a dumb way to write it, but without catalyst, you have some reaction A to P, dP dt is equal to K1 times A to the 1 power. We're assuming high pressure here. Right. And with catalyst, you find that the rate of formation of P is also dependent on A to the first power. You have no dependence on the catalyst. But you observe a different rate, K2. And by definition, K2 must be greater than K1. Okay? That's the difference between a catalyst and not a catalyst. You have a reaction that gives you some rate. It's got single, in this case, single order dependence. You maintain that dependence, kinetic dependence on the concentrations. The stoichiometry hasn't changed, but the rate has. Okay, and since the K is the only thing that's changing, that means that E sub A, the activation energy, is changing because that's the only thing that depends. So what I can do is draw a little diagram, of course, with a reaction coordinate, really simple. We have some uncatalyzed reaction, from A to P, with some activation energy. I've missed my mark. Delta G double dagger. And then when I apply a catalyst, which I'll write in yellow, the energies of A and P are exactly the same, but the barrier is just lower. So this is catalyzed. And this is uncatalyzed. Okay, so that's what a catalyst does. That's all it does. It doesn't change anything else. It doesn't participate in the reaction. I mean, it does participate in reaction, but not in stoichiometry. In fact, typically catalysts go through a cycle. I'll give you an example in a second. But a good catalytic process is one where you start with the catalyst at the beginning. It attaches to the reactants. It makes the reactants, and then undergoes some process to regenerate the catalyst again. So in some sense, the catalyst goes through a loop. A comes in, it goes through some process, spits A out, and then goes back to its original, or spits P out, product out, and then goes back to its original form to pick A up and continue on again. All right, so let me show you an example of a catalytic cycle. Of course, you guys maybe have learned some of those in intro biology or other classes. You know, there's the Krebs cycle, the metabolite. The Krebs cycle is a great example of a catalytic cycle. Let's find a nice one. This is a nice one. So here's an example of a classic the catalysis from inorganic chemistry. Oh, don't say that. So that's okay. So let's look at this catalytic cycle really quickly. So just an example. And I'll walk you through it. It's really simple.
Steps of time for every reaction, right?
No, of course not. This is just a specific reaction. So this reaction is taking ethane Oh, sorry, no, it's not. Sorry, this is the dehydrogenation. This is the hydrogenation of ethylene. So CH2 plus H2 to go with CH3 using a rhodium catalyst, RH catalyst. Okay, and so let's look at how this reaction works. So here's your molecule. Right, so here's your reactant molecule. Okay, so what it does is the first step it does is it attaches to the rhodium catalyst, right? So the rhodium catalyst connects to that double bond. This is an inorganic reaction. This is what's called an A-to-2 bond, where the rhodium attaches to the pi orbitals of the double bond, and it sits there holding it like this. The rhodium's like holding the two carbon atoms in their pi orbitals like this. And then what happens is that there's an H here on the rhodium, a hydride, that H inserts into the metal, into the molecule here. So what happens is that this rhodium, let me undo this a little bit. This rhodium is bonded to each of the carbons like this, and then this carbon grabs this hydrogen that's connected to the rhodium and plucks it off and breaks this bond here. And so now you have this ethyl group on your rhodium. And there's another H on that rhodium, and it happens again. Right? This H comes in and connects there. And now you have CH3, and you lose your CH3. Right? So there's your reactant. Right? And now your catalyst has lost the hydrogens that was on it. Right? And so now you have this rhodium catalyst. It's got a solvent molecule on it. It's got these special ligands called L. So some functional group. And a chlorine. And the system can swap out a ligand in the solvent like this. And then the H2 comes back in. And then the rhodium cleaves the hydrogen in two and then inserts itself in between the two hydrogens. And I've recovered the catalyst again. So now the H2 comes in and it gets split up. And the whole process happens again. All right, this reaction without a catalyst, I'll just tell you, I've tried it before, don't work. Like, you need a catalytic surface to do this reaction. Because in order for this to be feasible, you have to break a double bond and then break an H2 bond. And see, the first thing you have to do is break a double bond. You have to break H2 apart. And then somehow you got to get those two hydrogen atoms to react with this broken double bond. Right? You've got three bodies that have to come together and react at a specific orientation that everything connects. Right? Because this double bond, if you break the double bond, it's not very stable. You've got a biradical that's going to fall apart instantly. H2 is very endothermic. You got to break it apart. It costs energy, like 400 kilojoules per mole to break H2 in the gas phase. So this ain't happening. The only time that this happens without a catalyst is under high pressure and high temperature. You got to crank it up in a furnace. But catalysts like rhodium, and this is typically done with platinum as well, you can do this at room temperature, room pressure. This is something you can literally do at 298 Kelvin in 1 atmosphere. Right? Without the catalyst, that doesn't happen. But the catalyst provides a chemical way for us to promote the breaking of those bonds, right? The rhodium can insert itself between the H2, the bond between the hydrogens, to form rhodium hydride bonds. That might cost some energy, but it costs a whole lot less energy than it is to just cleave H2 by itself. And rhodium also is able to attach itself to the double bonds. That turns out to be exothermic. It's more than happy to do this coordination step. It's more than happy to do it. So what we've done now is, and then this insertion step and the reductive elimination steps, these are downhill. Right? So the slowest step is actually the oxidative addition to break the H2. So you have to do this at reflux typically, or sometimes you can do it at room temperature. Yeah, I should probably say this is reflux. It's probably not at room temperature, but it ain't at thousands of Kelvin. So it's done. You can do this in a flask. So let me put that there. This is done in reflux. All right, so it's in the 100 Celsius, 200 Celsius range. All right, so this catalyst doesn't change the chemistry, right? We take in H2 and ethylene and we spit out ethane. It's exactly the same reaction, but the rhodium provides us a stable surface, a stable material in which the processes we need, which is the cleaving of the H2 and the breaking of the double bond, it makes it easier for it to happen. Rhodium does that work for us. So the activation barrier is much lower, right? The kinetics change in some sense, right? Because now instead of it being two-step, one step, it's multiple steps that the rhodium does. But the idea is that you can try to think of this as one giant step right here, one giant step that happens at some higher energy, and that higher energy is much lower than it would be without the catalyst. Okay, so that's what a catalyst is. Right, this is a homogeneous catalyst, as we call it. This is what the inorganic chemists do. I don't want to really focus on this too much. It's a good example. Organic chemists love this stuff. Let's look at something more ubiquitous in catalysis. Something that's everyone has experience with this type of catalysis, whether you like it or not. Right. So the kind of catalyst I want to talk about, and I think it's going to take us 2 lectures to do it. We'll talk about it on Tuesday, are enzymes.
Yay.
Let's talk about enzymes today.
I don't know if that was.
Oh, I guess it depends on what kind of chemist you are.
Yeah.
If you're a biochemist, this is one of your favorite topics. If you're not, either you don't care or well, let me just say, we're not going to go too deep into the biology here, but rather I want to think about how, like, from a physical point of view, how does an enzyme work? How can we analyze the ability of an enzyme to catalyze a reaction? Right. So we should always, of course, define an enzyme. An enzyme is a protein or biochemical structure that catalyzes a biochemical reaction. All right, well, that's really stupid, but some sort of physical biological process. Right? There's tons of different examples of enzymes, which I won't go through at this moment. We'll do some more specific examples on Tuesday. But let's talk about enzymes generally. Right. So the enzymes, of course, are an extremely important part of biochemistry. Most pharmaceutical work, not every pharmaceutical development, takes advantage of enzymes. Some don't, some do. Typically, our targets for drugs are receptors and other types of proteins that perform some function in the body that we either want to amplify that function or we want to turn it off. Inhibiting versus agonist. An agonist is a molecule that makes an enzyme or some receptor or some biochemical structure act more aggressively, faster, more actively. We also have inhibitors, which do the opposite, so it slows you down. So there are different ways that we want to work with it. Right, but if we think about, for instance, a medicine, a drug that inhibits an enzyme, what we mean is we want to have this drug connect itself to an enzyme to slow the catalytic process it does in the body. Right, so the enzyme is munching on some molecule. Maybe it's, for instance, if a really great example is in clinical depression, right? One of the things that we take when we're clinically depressed is what's called a selective serotonin reuptake inhibitor. And a reuptake process is where your body, your neurons fire a bunch of serotonin across the axon, and you get through this loop where your nerves and your hormones, your receptors continue to make more and more serotonin. The process of it recycling the serotonin across the axon and through the neurons and then back into the system, right? You have this cycling loop for your serotonin. that gets overactive and it starts spitting too much serotonin out. When it gets absorbed by the other side of the neuron and it gets processed and then gets spit back out into the next transmission, you get a buildup of concentration of serotonin. And so your body gets flooded with serotonin and the neurons start to shut down. Right? That you get overwhelmed with that, your body. And so we take selective serotonin reuptake inhibitors, which binds to that serotonin receptor that recycles the serotonin after it goes through its biochemical process and slows it down to slow down the recycling rate of the serotonin in the neurons. And so that starts to balance out your muscle cycle. And of course, there are other types of things where people have very low serotonin creation. They take a different type of drug, which is an agonist, which kicks in your serotonin development. I don't think depression is typically associated with that. Typically, it's associated with an agonism of another neurotransmitter called norepinephrine. Typically, you want to kick that in the food or dopamine. So there's lots of different ways, right? Sometimes you want to slow things down. Sometimes enzymes are too effective. Sometimes they're not effective enough anymore. So let's think about how an enzyme works, right? How does an enzyme do its job? We don't understand how it does its job. It's hard to manipulate that. And there's two kind of overarching mechanisms that people use to analyze enzymes. One is kind of old-fashioned, but it's really, really nice to think about. And the other one's a little more complicated, but more accurate. Yeah, basically. And we'll understand very quickly why that will be. I'll make sure to emphasize that. So two characteristic mechanisms.
Right?
Oh yeah, you better believe it. Jeez. Do you know what the other one is?
I can't recall,
Okay.
but it's like it changes based on what it needs.
Exactly. It's called induced fit.
Oh yeah.
You got it. You got it. So this is probably a review for some people. You took medicinal, right?
No, I'm taking that next semester. I took bio.
Oh, okay. Well then, yeah. So that explains it. All right. So the first one, so the general scheme for an inhibitor or for an enzyme is we take an enzyme, so I'll call E. We add to it a substrate, right? It's the thing that the enzyme binds to. There is an association of the two. That's an equilibrium. So we have an association step that we mark as Ka, and the reverse would be Ka prime. Right? And that forms our enzyme substrate complex, ES. Right? And then the enzyme is now bound to the substrate and it starts doing its job. And so it will eventually, at some other rate, Kb, spit out the products and return back the enzyme. Okay, so classic catalytic cycle. Enzyme and substrates grab by an enzyme does something, it spits out the product, and the enzyme's back for the next step. Okay, so what's an example of this? Well, many of you are probably very aware of you've experienced this enzyme process. You might not have known it. But there's a really famous enzyme called ADH. This is called alcohol dehydrogenase. So enzyme in your body. I'll pull up a picture of it in a second. Right. And what does alcohol dehydrogenase do? Well, it takes ethanol and spits out, well, no, actually it does spit out water, but in particular, it spits out acetaldehyde plus ADH. Right. This is the process of this is the protection of your body from alcohol poisoning. It's how we process alcohol. Right? Our body takes alcohol, which is a polar solvent, It dissolves in your blood readily. It's miscible with water. Gets mixed in your blood, and it converts it into acetaldehyde, which is not which is much less soluble in water than you just piss it out. It gets renally extracted, right? So this is extracted via the renal gland, right? And you just piss out the acetaldehyde. That's why when you drink a lot and your pee smells really funny the next morning. One of the reasons is it's because of the acetaldehyde. Acetaldehyde is a very characteristic smell. Very, very characteristic. There's other things that fall into your pee. There's urea, there's nitrogen decomposition products that also are smelly, but a large amount of it is acetaldehyde. If you're diabetic, for instance, another thing that can happen is it can over-oxidize and form a ketone. You get ketosis. That's when if for instance, if your urine smells sweet, it's indicative that you're not processing sugars and you're actually producing acetone and the propyl version of it as well. And that's a sign of ketosis and also diabetes. Okay. Interestingly, you may know this, may not. If you replace that with methanol, right? Methanol kills us. And the reason why is because of the dehydrogenation project of our product. So you form formaldehyde. Formaldehyde makes you blind. It binds to your brain very effectively, crosses the blood-brain barrier, and eventually kills your eyes and your nervous system and your renal system, and you're dead.
Lovely.
Yes, but acetaldehyde, just that extra methyl group, makes it much harder to cross the blood-brain barrier, and you just pee it out harmlessly. Well, very interesting how methyl groups can make a difference here. Okay. So there's two mechanisms that we use to describe these processes. And already spoiled by Angie over here, but that's okay. The first kind is called lock and key. And I'm just going to draw this pictorially. We can think of the enzyme as a little Pac-Man. So here's my enzyme. Right, and my substrate is a little pizza slice that fits right into that hole. So here's my substrate. Right, and that's going to fit in there. Right, and you can think, well, if it's the right size, right, this is a fixed hole, what we call a binding pocket. What we say is that binding pocket is as a specific size. And so if the substrate is the right size, if it's the Goldilocks substrate, it's going to fit right in. Right? We get a nice tight binding. Where this little pizza slice locks right in. Right, like that. So we have a good fit. But there might also be some other substrate that comes in that's too small. So this is where the selectivity of these enzymes come in, is that the pocket, right? Maybe it's this small, right? This is going to not go in. Too small. Too small, right? So the idea is that you have a pocket that fits the enzyme, or sorry, that fits the substrate perfectly. It's designed through some sort of evolutionary process, right? It's very interesting, right? How do proteins, it's actually somewhat of an unsolved problem, how do proteins find that right orientation to fit the right thing? Lots of interesting evolutionary engineering arguments associated with that. The idea is that you have a perfect hole for the perfect molecule. Right? So the enzyme's binding pocket is fixed, but designed to fit specific molecules or specific substrates. Right. And of course, the idea is that what happens is that this process is our reaction. Right, so the reaction occurs and we're left with our original enzyme and a new molecule, our new product molecule, which I'll make a little kind of squiggly and all messed up. So our new molecule P. Right, so we have S in here, we have ES, and then we have E plus P. So this was kind of the way that biochemists thought about substrate interactions and enzymes for a long time. Made a lot of sense. And as we'll see, the kinetics, when you do this lock and key analysis, the kinetics actually make sense. And they give you things that give you quantitative answers about biochemistry. But there are enzyme reactions and substrates that are very efficient for enzymes, where when you do the structural analysis, they don't seem like they fit properly. That something must happen to the enzyme that when the substrate comes in, it adjusts its size to kind of fit it. Like Pac-Man opens his mouth a little wider, closes a little bit, depending on the substrate that comes in. So the problem with this idea, the lock and key, is that you only have so many enzymes in your body, and if they have fixed pockets, then the scope of the number of the substrates that they can deal with are very limited. Right? In some sense, you could think, okay, one enzyme for one molecule. Right? If ethanol is the right size for ADH, you put methanol in there, maybe doesn't like it. Which is actually true.
Also, then, like, if you have too much of something, then how do you cause the enzyme?
So we'll get to that. So that's another question. So it's another issue is if you drown yourself in substrate, how does the enzyme keep up? Is that what you're implying?
Yeah.
So that's a great question. We'll answer that.
Or the opposite.
Or the opposite.
If it's too much
But
product.
let's think, for instance, right, you have alcohol dehydrogenase, and we use lock and key, and we say it fits ethanol perfectly, and then you drink rubbing alcohol. Well, rubbing alcohol is a much larger species. It's not going to fit in that pocket, but what you do find is that ADH is somewhat a bit effective at decomposing and dehydrogenating rubbing alcohol, isopropyl alcohol. Right? And so the idea is that the binding pocket isn't exactly fixed, that it may adjust a little bit. And that's going to change your kinetics, because now what you have is an additional step where delta G changes because the enzyme changes its structure slightly to stabilize more. So let me see if I can jam this in the corner. I'm going to get rid of this so I have some space. The other example is what's called the induced fit mechanism, or induced fit binding, right? Where your enzyme binding pocket is a little fuzzy. Right? It's got a general size, right? But it can adjust based on the size of the substrate that comes in, right? So you could have this really big substrate, right? This is our big chungus substrate. And they can come in, or we can have this little tiny molecule, little Dorito, and it can come in, right? And what the system does before it enzymes is it isomerizes to adjust for the size of the binding, right? So we have our substrate, our enzyme adjusts its hole slightly to fit our little Dorito, closes up a little bit, right? But it can also widen the hole like this to fit our large substrate as well, right? And then proceed to release the product large plus enzyme, or P small plus enzyme. right? But there's an additional, right? There's an additional additional energy that's accounted for it. Right, so how does the energy change in this system? In lock and key, we have a substrate and an enzyme that aren't moving. They're fixed in position and fixed in structure. So they both have a delta G of formation. So you have some delta G of binding. Right, and then you have some delta G of reaction, right? So there's just two Gibbs energies to think about with lock and key. There's some binding energy. It tells you how willing it is to take that substrate. The substrate's too big or too small, G is going to be positive. And then we have some reaction delta G. Super easy. Very convenient. But here we have two different energies going. We have a binding energy, but we also have an energy associated with the structure of the enzyme change. So there's two energies that are happening here. One is that you have delta G bind. It still binds, but you also have delta G of the fit. Oh, let's see, what would I want to call that? Like, you know, the readjustment. Yeah, I don't know what to call that. Isomer. Yeah, okay, delta G of change, right? So you've got two now, right? And depending on the size, depending on the size of the species, you're going to have a different G binding and a different G isomerization, because this enzyme is appreciably different from this one. They have different structures. Well, I mean, they're still the same sequence, but in some sense they move the binding pocket. The energies change a little. So this enzyme here is different from this one. So you could write, for instance, if this one is ES, this one down here is some other enzyme E prime S, right? It has a different structure. So there's an energy difference not only between the bindings between E and S, right? This might bind better than this one. It might, in general, prefer little Doritos over big chungus does. Might prefer them the same, who knows? But there's also some energy requirement that you have to take this and stretch it and deform it into this position, stretch and deform it into this position. And so now we have lots of different energies that are bouncing around. Right? And these also may lead to different delta G's of reaction. Right? You get some delta G of reaction here to kick out the products. And you get a delta G of reaction that's different here to kick out these products. Right? So it's a more complicated problem. But it's also more accurate, right? This allows my enzyme to have more flexibility. It has multiple properties and multiple features. It does multiple different things. It's not just a dumb little Pac-Man. It's a dynamic Pac. Mrs. Pac-Man versus Mr. Pac. So this is a much harder thing for us to measure. All right, we have to be very careful. And the kinds of things that biochemists do to understand induced fit is really interesting. They do things, for instance, like if they have a sense of where the binding pocket is in a protein, they'll change one of the residues, one of the amino acids in that binding pocket, to some other amino acid through protein engineering, and observe how the enzyme kinetics change. Right? If you've got some little amino acid here that's connecting to your substrate through a hydrogen bond, and you remove that, it's going to change the kinetics. And so what they do is they say, hey, I'm going to make some mutants of this enzyme, and I'm going to put it with little Doritos, and I'm going to put it with big chunguses, and I'm going to keep making different mutations, and look at how the enzyme efficiency changes as a function of how we change the enzyme in its pocket, induced fit, and the molecules that go into it. And you can get a sense, right, of how flexible or what that system is doing by looking at how the kinetics change as a function of the structure of the enzyme. I really will try on Tuesday to show you some pretty pictures of these. Okay, so we don't have enough time to really dig into the kinetics of this. But we have a really interesting idea here. What can we learn from this? Well, what we can learn with a little bit of math, a little bit of work, we can come up with a really simple kinetic law that allows us to quantify the behavior of this enzyme. Because what we don't know is, we don't know that, for instance, that this enzyme does something, right? But we want to understand again the kinetics of how it works, because then we want to do manipulations to it, right? We have an enzyme that does some process that is health wise not good, right? So we need to apply another medication to it, some drug to it, to manipulate its behavior, right? Maybe we want to inhibit and slow down the catalyst. Maybe we want to speed it up. And if we can understand how a catalyst binds to its substrate and how much substrate it needs in order to have it completely bound and be completely saturated and working at full efficiency, we can learn, turns out we can learn and predict what's going to happen to the enzyme when we start to manipulate it with inhibitors and agonists with our drugs. So we can learn something about drug action and how a drug affects an enzyme by studying the kinetics of that enzyme in the presence of the drug. And it will require a very, very simple kinetic argument that uses the solid state, or not the solid state, the steady state approximation. We'll get this equation that teaches us about the raw kinetics, the rate at which things bind. And then what we'll look at is, as we manipulate things, we can see how the kinetics change as we add our drug, our agonist, or our inhibitor. And based on how the kinetics change, we can identify whether that drug is an inhibitor, an agonist, or a replacement for the substrate. Does it just replace the substrate entirely? Or does it manipulate the enzyme in such a way to affect the way that it interacts with substrate? Right, so we'll talk about that mechanism on Tuesday. We'll look at some examples of some enzymes, some binding pockets, the kinetics and the energetics of this process. We'll look at some, we'll find some good drugs that we can look at. If anyone has a drug they really like, you can send me an email with that suggestion. We'll find some interesting biochemistry about it. Yeah, so let's think about that. Anyway, if I don't see you on Tuesday, have a lovely holiday break. Otherwise, I'll see you on Zoom, or I'll see you in here, or most of you I'll see you tomorrow. Have a good one, guys.
Have a good one.
Thank you.